May 1964. In a field in Holmdel, New Jersey, two radio astronomers named Arno Penzias and Robert Wilson are calibrating a 20-foot horn-shaped antenna, originally built for satellite communication, for a much more sensitive kind of listening. Instead of silence, they keep picking up a faint, steady hiss. Same intensity in every direction, same intensity in every season. They check nearby New York City for interference. They check for leftover radiation from a nuclear test 2 years earlier. They even find a pair of pigeons nesting inside the antenna and physically clean out what they later describe, very politely, as a white dielectric material. The hiss doesn't go away. Whatever it isn't coming from Earth. By the end of this video, you'll know exactly what that hiss turned out to be, why it proves you can never actually see the moment the universe began, no matter how good your telescope gets, and about a specific, oddly cold patch of sky that even the scientists who mapped it still can't fully explain. Here's where most people get the Big Bang wrong before the video even starts. They picture an explosion, a single point in the middle of empty space, detonating, throwing matter outward into a void that was already sitting there waiting for it. A bigger, older version of a firework going off. That's misconception number one, and it's less like a small error and more like starting the whole story facing the wrong direction. The Big Bang wasn't an explosion in space, it was the expansion of space itself, everywhere, all at once, and there was no empty void outside it for anything to expand into. Picture dots painted on the surface of a balloon, not inside it, on the rubber itself. As you inflate the balloon, every dot moves away from every other dot. Pick any dot, and from its point of view, all the other dots are receding, which means there's no special dot at the center. Every point looks like the middle. That's the actual geometry of cosmic expansion. Not matter flying outward from a center into pre-existing space, but the space between everything, everywhere, stretching at once. Run the balloon backward, and you don't find a point where the explosion happened. You find a moment when the whole surface was compressed into an infinitesimally small area, which is a very different claim than there used to be a bomb here. That naturally raises the question every version of this explanation eventually runs into: what was there before the Big Bang, if not empty space waiting to be filled? The honest answer is that physics doesn't have a confident one. Time itself, as best current theory can describe it, appears to be a property of this universe, not a stage it happened on, which means asking what came before may be a little like asking what's north of the North Pole. It's not that the answer is being withheld, it's that the question may not point anywhere yet. None of that was purely theoretical guesswork, either. In 1929, the astronomer Edwin Hubble, working at Mount Wilson Observatory, measured the light coming from distant galaxies and found that nearly all of them were redshifted. Their light stretched toward longer wavelengths, the same way an ambulance siren drops in pitch as it speeds away. The farther away a galaxy was, the more its light was stretched, and the faster it appeared to be receding. That relationship is exactly what you'd expect if space itself were expanding, carrying galaxies apart the way the balloon's rubber carries its painted dots apart. Hubble's observation gave the expanding universe idea its first real evidence, decades before anyone had detected a single photon of the cosmic microwave background. The two discoveries, 35 years apart, were answering the same question from opposite ends. Hubble showed the universe is expanding right now. Penzias and Wilson showed what that expansion implies, about how hot and dense everything used to be. So if there was no explosion to look at, what were Penzias and Wilson actually hearing? They didn't know yet. What they did, once they'd ruled out every earthly explanation, was call Princeton, specifically the physicist Robert Dicke, whose team, including Jim Peebles, Peter Roll, and David Wilkinson, was in the middle of building a detector to search for exactly this kind of signal. Dicke's group had worked out, on paper, that if the universe really did begin in an extremely hot, dense state, it should have left behind a faint bath of radiation, cooled by billions of years of cosmic expansion down to a few degrees above absolute zero, a relic they called the primeval fireball. They were racing to build an antenna sensitive enough to detect it. Penzias and Wilson had accidentally beaten them to it. The story goes that when Penzias called Dicker to describe the mysterious hiss, Dicker listened, hung up, and turned to his own team, who had spent months designing a detector to hunt for exactly this signal, with a line that's been repeated in physics classrooms ever since. "Well, boys, we've been scooped." A team racing to find the afterglow of creation lost the discovery to two radio astronomers who were just trying to get rid of static. The two teams published their papers back-to-back in the same 1965 issue of the Astrophysical Journal. Penzias and Wilson reporting the measurement, Dickey's group explaining what it meant. In 1978, Penzias and Wilson received the Nobel Prize in Physics for the discovery. Neither of them set out to test the origin of the universe. They were trying to calibrate an antenna, and they ran into the oldest light that has ever reached anyone's instruments. And this wasn't a one-instrument fluke that later evaporated under scrutiny. In the 6 decades since, ground-based radio telescopes, high-altitude balloons, and 3 separate dedicated satellite missions have all pointed at different patches of sky, using different detectors built by different teams, and all of them keep finding the same faint bath of microwaves, arriving from every direction at once. That kind of independent, repeated confirmation is what separates a real cosmological discovery from a quirky one-time reading nobody could reproduce. Which brings up the second, more common misconception, the one baked right into the phrase, seeing the Big Bang. Most people assume that with a strong enough telescope, you could, in principle, look far enough back to see the actual moment of creation. You can't. Not with light, not ever, no matter how the technology improves. And the reason why is the most important idea in this whole video. For the universe's first roughly 380,000 years, it wasn't transparent. It was an opaque, superheated plasma, a soup of free electrons and protons too hot to combine into atoms, and any photon trying to travel through it got scattered almost immediately, bouncing from particle to particle the way light bounces around inside thick fog or inside the core of the sun. A photon born in that plasma didn't get far before smashing into an electron and changing direction. There was light everywhere, and none of it could travel in a straight line. Then, around 380,000 years in, the universe had expanded and cooled enough, down to roughly 3000 Kelvin, for electrons and protons to finally combine into stable, neutral hydrogen atoms. Cosmologists call this recombination, and the moment it happened, the fog lifted. Photons that had been trapped, scattering endlessly, suddenly had a clear path. For the first time in the universe's history, light could simply go somewhere. That boundary, the last moment photons scattered off free particles before the universe went transparent, is called the surface of last scattering. It's the oldest light it is physically possible to see, not because we lack the technology to see further, but because further back, there was no unobstructed light to receive. That's not the birth of the universe. That's the moment the universe finally turned the lights on. There's a nearer, smaller version of this same limit that you've already experienced without thinking about it. You can't see into the sun, past its glowing surface, into the layers where fusion is actually happening. You only ever see its photosphere, the outermost layer where the plasma finally thins out enough for photons to escape in a straight line. Everything deeper is opaque, scattering light the same way the early universe did. The cosmic microwave background is that same idea, scaled up to cosmic size. Not a window into the universe's interior, but the surface where it finally stopped being one continuous fog. Those specific photons have been traveling for about 13.8 billion years since. Cosmic expansion has stretched their wavelengths the entire way, from the visible and near-infrared light they started as, down into microwaves, dropping their effective temperature from roughly 3000 Kelvin at emission to 2.725 Kelvin today. That afterglow has a name, the cosmic microwave background, the exact hiss Penzias and Wilson picked up in a field in New Jersey, still arriving from every direction right now. Quick pause here, because it's worth sitting with what you just heard before moving on. There's a hard physical wall, not a technological one, between us and time zero, and it sits at 380,000 years in. If this reframing of seeing the Big Bang is new to you, hitting the like button helps this reach more people who'd want that reframe too, because there's more to that leftover light than just it exists. And the next part is where the story gets its second Nobel Prize. In 1989, NASA launched a satellite called COBE, the Cosmic Background Explorer, built to answer two questions about that leftover radiation. Does it actually match the smooth textbook shape a genuine relic of a hot early universe should have? And is it perfectly uniform, or does it have structure? Two scientists led the two halves of that mission. John Mather headed the instrument that measured the radiation spectrum. In January 1990, at a meeting of the American Astronomical Society in Virginia, Mather presented the result to a room of over 1,000 astronomers, based on just 9 minutes of the satellite's data. A curve that matched the theoretical prediction for a perfect black body so closely that the audience gave him a standing ovation on the spot. Later analysis tightened the measurement to within 50 parts per million of the peak intensity. It remains one of the most precise confirmations of a theoretical prediction in the history of physics. The second half of COBE, led by George Smoot, had a harder job, finding tiny variations in that radiation's temperature, differences of about 1 part in 100,000, scattered across the sky in a faint mottled pattern. Those variations weren't noise. They were the seeds, the earliest fingerprint of the slightly denser regions of the early universe that would go on, over billions of years, to collapse under their own gravity into galaxies, stars, and eventually you. Mather and Smoot shared the 2006 Nobel Prize in Physics for the discovery. At the 1992 press conference announcing the anisotropy result, Smoot was widely quoted describing the ripple pattern as being, for anyone religiously inclined, a bit like seeing the face of God, a line that made headlines around the world and also drew criticism from other physicists for overselling a genuinely careful piece of data analysis. The measurement didn't need the metaphor. 1 part in 100,000 is a small enough variation that finding it at all, buried in satellite noise, was already the achievement. That same data, refined further by two later missions, WMAP through the 2000s and the European Space Agency's Planck satellite, whose final results were published in 2018, gave cosmologists the most precise measurement yet of what the universe is actually made of. And this is misconception number 3, maybe the most humbling one. Most people assume the universe is mostly made of the stuff that's familiar. Stars, planets, gas, us. Planck's data says ordinary matter. All of it, everything made of atoms, accounts for about 4.9% of the universe. Dark matter, which doesn't emit or absorb light and is only detected through its gravity, makes up roughly 26.8%. The remaining 68.3% is dark energy, the mysterious pressure driving the universe's expansion to accelerate. The same data set Planck's age of the universe at 13.82 billion years. Dark matter and dark energy aren't the same mystery wearing two names either, even though they get lumped together constantly. Dark matter behaves like matter. It clumps, it has gravity, it holds galaxies together against forces that should tear them apart. It just doesn't interact with light. Dark energy doesn't clump at all. It's spread evenly through space, and it pushes outward. And it's the reason the universe's expansion isn't just continuing, but accelerating. Two separate unsolved problems, both discovered largely through their effect on the same leftover light this video keeps coming back to, which loops back to something you may have already heard, phrased with more confidence than it deserves. You probably encountered the specific claim that about 1% of the static on an old unplugged analog television was the afterglow of the Big Bang, the cosmic microwave background, arriving through your antenna along with everything else. That's misconception number 4, and the correction is subtler than true or false. The general idea is real. An old TV's antenna, tuned to an empty channel, was picking up genuine ambient radiation, and the cosmic microwave background was one contributor among several, alongside terrestrial radio interference, atmospheric noise, and emissions from the Sun and the galaxy. But that specific 1% figure isn't a measurement anyone actually made. It's an estimate that migrated from writer to writer, popularized in books like Bill Bryson's A Short History of Nearly Everything, repeated so often it started sounding like a citation. The charming version of the fact that ordinary people spent decades staring at the oldest light in the universe without knowing it is true. The precise number attached to it isn't something science actually measured. Somewhere between the static and the standing ovation, a real discovery about the origin of everything got flattened down into a bar trivia stat, and the flattened version is the one that stuck. So, not an explosion, no center, a hard 380,000-year wall on how far back light can show you anything, a universe that's 95% stuff we still can't directly explain, and a famous fact whose specific number was never really pinned down. Every one of those corrections points at the same underlying idea. The leftover light from the early universe is real. It's sitting in your data every time a radio telescope looks at the sky, and it is far stranger and far better measured than the popular version of the story usually lets on. Go back to that field in Holmdel. Penzias and Wilson weren't looking for the birth of the universe. They were trying to get rid of a noise they assumed was a flaw in their equipment, cleaning out pigeon droppings, checking for radio interference from a city 40 miles away. And the whole time, the flaw was the single oldest thing either of them would ever detect. They didn't discover the Big Bang. They discovered the moment, 13.8 billion years ago, and 380,000 years into the universe's existence, when it stopped being opaque and let its own light go. That's not the birth of the universe. That's the moment the universe finally turned the lights on, and it's been arriving from every direction, at every point in space, including the one you're sitting in right now, ever since. If this is the kind of thing that makes you want to look at static, or the night sky, or just the number 13.8 billion a little differently, that's exactly what this channel is for. Subscribe if you want the next one of these. Tell me in the comments which part of this actually surprised you, and if you made it this far, a like helps this find the people who'd get just as much out of the balloon analogy, finally clicking as you just did. One more thing, before you go, that never came up anywhere above. When scientists mapped the cosmic microwave background in detail, they found something they didn't expect, a single patch of sky in the direction of the constellation Eridanus, roughly 70 millionths of a degree colder than everywhere around it. Small in temperature, but enormous in scale, spanning what could be 500 million to a billion light years across. Both the WMAP and Planck missions confirmed it independently, and the odds of a patch that large and that cold showing up by pure chance under the standard model of a smooth early universe are only about 0.5%. The leading explanation is that it's the shadow of an enormous, mostly empty region of space along our line of sight to it. A supervoid, since confirmed by a separate survey, so much emptier than its surroundings that light passing through loses a fraction more energy than it should. But leading explanation isn't the same as settled. 2 decades after it was first spotted, the cold spot is still one of the only genuine anomalies in an otherwise remarkably well-explained universe. A single cold patch in the oldest light there is, still waiting for someone to fully explain it. Which, if you've ever wanted a reason to come back for a follow-up video, is exactly what one is for.